Moving down to complex number crash course, we have a question like x squared plus 1. And okay, if you solve this, you have for x squared equals to 0, you are going to find yourself having x strictly greater than or equals to 0. But in case you add a 1, you are going to have x being greater than 0. But the problem will come in case you want to solve this question. You are going to find yourself having x squared is equals to negative 1. And actually, this is somehow trash. We don't know exactly what's this. I'm going to conclude that mathematicians actually find problem anyway because they try inventing something that was supposed to be ignored because they are trying to solve something that we could just ignore this question because it's actually not real. But since complex number is quite amazing and important, we need to solve it. Let's move on. If you have x cubed minus 15x minus 4, the first thing that comes into your mind is substituting maybe 4 here. You substitute 4, 4 being a root, 4 is a root, and you substitute 4 here, 4 cubed minus 15 times 4 minus 4. That will exactly give you 0. But the question now comes when you want to solve for the other roots of this cubic polynomial. Moving on, you have x cubed minus 15, x minus 4. You are going to use a Cardano principle by first of all writing this in a form what? X cubed plus px plus q. P representing 15, negative 15, Q representing negative 4. I'm going to substitute in the Cardano's formula. This is the formula. And you substitute here. You're going to be having the square root of a negative number. Pause here. You are going to explain better what is happening or what are you going to do when you have the square root of a negative number. Okay. This can just be set as trash, no, but you have to solve it because this is quite important because you're going to have a value by solving it. Okay, let's dive into the complex number. Okay, starting with complex plane. If you have a complex number that is a plus bi, okay, you have this a, b being the I being the imaginary unit and multiply the imaginary part. Okay, and I squared is equals to negative 1, a being the real part and b being the imaginary part. Okay, and the combination of this make a complex number where a and b are real numbers actually. Okay, in an imaginary z plane we have here. Okay, you have an imaginary plane here. That is a normal plane. You can plot this this on the plane by having z is equals to a plus bi. You plot this on this plane. And you are going to have a being this part and b being the other part. Okay, and you have a point a b. Up here being the imaginary and down here being the real part as earlier said. Okay, the real axis and up there being the imaginary axis. You can have in a polar formula in a polar coordinate here having the modulus that is r and the argument that is theta. And we can directly plot this z is equals to a plus bi only in a polar form on a z plane. Okay, moving on to knowing more about angular representation. If you have only the modulus, you are going to have the modulus like for this one, for in the first quadrant, that may be 4. If you have like 4, something like that, because square root a squared plus b squared, you have the modulus. I'm going to explain better about this in the next section. We are just proceeding. Okay, having a modulus that is 4, we can also have you have also the same modulus 4 here and here. But you need an independent value that is theta to know exactly the angle of inclination of this. Because if you don't know the angle of inclination, you are not exactly going to know how it looks like. I'm going to explain more about this angle better. Just digest it for the moment, pause where you don't understand, and read well. Okay. We notice that at the numerator here, we have the positive, and at the denominator, we have the negative section. Okay. Where it ranges from negative pi to pi there. Okay. In the polar form, you have this, and you proceed by plotting directly. You have a and b at the point AB, and in the polar form, you have r and theta, the angle theta. That's how it is formed in the polar form. And from where you can directly deduce that a is equals to r cos theta because you have a here, a, b here, and a here. And a is equals to r cos theta from basic principle of trigonometry because from this angle, here is theta, a. Okay, we are going to have what cos theta is equals to what? A all over r being this hypotenuse, and a is equals to r cos theta. As normal mathematics, and on that side sin theta is equals to b all over r, and that is the same thing as b is equals to r sin theta. Okay, therefore z is equals to what? A plus bi, and you can directly deduce that z is equals to what? R cos theta plus I sin theta. That's amazing. Yeah. Okay, because a is r cos theta and b is r sin theta, including this I because That make it a complex number. And to solve for r, from the basic principle I put in, that will be a square, this a and b, that will be a square plus b square. Exactly. And the square root of that, because from Pascal triangle, we have r square is equals to a square plus b square. Sorry for the handwriting. That's amazing. We proceed by having tan theta is equals to b on a. That's the angle, the imaginary part over the real part. Therefore, theta is equals to tan inverse of b on a. That's exactly the answer. But do you know that this value only occur or only happen in case you're in the first quadrant? Yeah, because in the other quadrant, something might change. I'm going to explain better. Just stay tuned. And this theta ranges from negative pi on 2 to pi on 2. Okay, is it the angle from negative pi on 2 to pi on 2 at this point? Okay, therefore, y is equals to arc tan theta ranges from negative pi on 2 to pi on 2. Okay, this is somehow coinciding, because in another quadrant, what would be the angle, because you're going to somehow add 2 pi at some point to have the exact value. Okay, that is not a cup of tea for the moment. Then move on. Okay, angles representation. You're going to be representing angles on the z plane. You have the first quadrant, the second quadrant, the third, and the fourth quadrant. How are we finding the angle at each quadrant? Okay, in the first quadrant, the angle is what? Tan inverse of b on a. That's exact, because you're in the first quadrant where a and b are positive. Okay, if you extrapolate this here, are you seeing it? Yeah, we extrapolate this r here, because r can just extrapolate here. What will happen at this point? Will the angle be the same? That's the question. No, since we are in another quadrant, here we have negative and negative. The angle here will be what? Arc tan a b on a minus pi, because we are in another quadrant and we have a pi here, and we just move on. So as to complete it, so as to have the exact angle. Okay, because if you just put that is arc tan a plus b, it will be exactly saying that you are at this level, although that's not correct. In this second quadrant where all a and b are negative, where is negative a, negative bi, here's that quadrant, we have to subtract, have a minus pi. Okay, then moving on to this other quadrant here will be exactly being the mirror image of this other man. Okay, here is positive and negative, positive here and negative. Here is exactly the mirror image of it. That will also be arc tan b on a. But now the question comes where we extrapolate to this point. That is the second quadrant. The second quadrant, the angle theta. What's the angle theta? Here we have both positive and negative, respectively, because here is negative a plus ib. Here is what? Negative bi, that is a minus bi. Here is what is happening. Okay, and we have what? The angle plus pi. That is what happened at that point. The angle plus pi. Let them therefore write how the equation look like at every quadrant. In the first quadrant, here the equation look like what? Z is equals to a plus bi. In this fourth quadrant, the equation look as what? Z is equals to a is positive and b is negative minus bi. In the second quadrant, how does it look like? It look as what? You have a negative, that is negative a plus bi. And the third quadrant, we have what? Negative a minus bi. Exactly, that's what we have concretely. For a complex number, we have the normal way of representing that is based on its real and imaginary part. That's exactly how we represent complex numbers. Okay, here is the real and here is the imaginary part. At the point A being this one and B being the yellow one as a color present. And you can represent a complex number in polar form. Here is just like a recap. We are just trying to recapitulate everything we did in this chapter 1. Okay, in a polar form, we can represent in terms of r and theta. R being the modulus and theta being the argument. Here we are focusing on the first quadrant. Hope you know how the angle varies in different quadrants. You can just put this in your head and know exactly what happened. Here the modulus and the argument. Okay, we have the point r and theta. Okay, moving down to chapter 2. Chapter 2 will be talking about the Euler's formula. Do you know Sir Euler's? I think you know about him. Okay, Euler's formula is in the form e to the I theta is equals to cos theta plus I sin theta. Oh yeah, I know you're asking yourself, where is this amazing formula coming from? Just stay tuned. We are going to dive extremely hard into this formula. Yeah, we are going to be proving this Euler's formula using 3 different principles. Let's start with the power series. Okay, to prove that this formula actually is correct, e to the I theta is equals to cos theta plus I sin theta. You're not just going to go online and copy this formula and come and paste here and start applying anyhow. You need to understand the basic of complex number. Because someone asked me, he wants to understand this, and I will need for that. Okay. And the power series state that e to the I theta is equals to a summation from n equals to 0 to infinity of I theta to the power n all over n factorial. And we then reduce this as what? This. Okay. Looking at this, we have the 1 plus I theta. You see, the part we are putting in yellow because we are going to remain in I, because I square is equals to -1. I cube is equals to, just guess, -1 times I. That's negative I. I to the power 4 is equals to 1. That is why you see at this point, you have I square, this will turn, you have an I square here, this will turn to 1. Okay. Here's I cube, you have an I here, I4, here will be 1. Here is -1, so here is I to the power 5. That is I4 times I, that is 1. You see, that is how it's going to turn around, and you're going to just simplify further. And simplifying, we are going to bring the like terms. The term in I, on the one side, there's the imaginary, and the real part on the other side in blue, and the imaginary part in yellow. Okay, let's just talk again. I square was -1, I cube, negative I to the power 4, 1. And we use this principle to derive here and simplify further. I'm going to be having I into all of this. That's amazing. That's becoming very good, I think. Therefore, we can just simplify this to cos theta, because from trigonometry, I know you know about trigonometry. Cos theta is equal to what? 1 minus theta all over 2 factorial plus theta all over 4 factorial plus theta all over that minus theta all over 6 factorial, and so on and so forth. That is on up to infinity, and we take this as sin theta. This is how sin theta look like, 7 and all those stuff. Okay, that's amazing. It's just periodic, moving from positive to negative. That is how cos and sine does. Okay, they are periodic, moving from positive to negative. They are teaching. Okay, and we can then conclude that the Euler's formula is correct, because e to the I theta is equals to cos theta plus I sin theta. We use the power series to prove this, and that's correct. Meaning our formula was not just copied from the net, it was derived. Basically, let's use another properties to derive this. There is a differential property. If you have g of the theta of e to the I theta, you are going to be having I e to the I theta. That's critical. That's exactly what you have from basic principle of differentiation, because we are going to differentiate. In terms of e, you differentiate the numerator and copy it here. That is I in terms of theta. And you copy it back. That is e to the I theta. Okay. Therefore, and what about differentiating cos theta plus I sin theta? You discover that if you differentiate cos theta plus I sin theta, you're going to have I cos theta minus I sin theta. I'm seeing something, which means differentiating with respect to this is just like multiplying by an I, because you have cos theta plus I sin theta. Multiplying this by an I, you are going to have I cos theta minus sin theta. Because I square actually is -1. Okay, we're having this. Representing this on the plane. Okay, I'm going to be having that. Seeing that, okay, this will be exactly, if you have cos theta that is positive and positive, we move then to negative. Okay, and to just derive and so on and so forth. Then move to another method in proving this using the method of limit. I'm going to explain this better after. Okay. From Euler's formula, e to the I theta is equal to cos theta plus I sin theta. Actually, well, hence having this, we are going to have theta is equal to pi. Therefore, cos pi is equal to -1. That is a typical example. And sin pi is equal to 0. Therefore, e to the I pi is equal to -1. You know about the beautiful math equation from Euler's, yeah, that's how it was derived. Because if you take theta being equals to pi and substituting here, cos theta is -1, and sine pi, okay, theta is pi is equals to 0. And eventually having -1 as our final answer. That is a recapitulation of Euler's formula. Moving then to chapter 3. In chapter 3, we're going to be talking about what? Operation of complex number. Also, complex number is just like a set of numbers on its own. We carry out addition, subtraction, multiplication, division, dot product, cross product, all those stuff happen. But here we're going to just focus on some basic point of it. At a point, you can just treat the complex number as a vector, because at a point it just looks like a vector. But for the moment, we're going to focus just on the basic point. Let's move on. Okay, moving to addition and subtraction. All what you have to do is to add the real and add the imaginary part. We just use different colors so as to better know. A is the blue one are the real and the yellow are the imaginary point. You just add the real A plus A2 and you add the imaginary that with an I outside. And in case of subtraction, it's exactly the same thing. Add the real, you subtract the real and subtract the imaginary. That's typical. You don't have to stress here. That's very easy, sharp word. It's just like a 1 plus 1. Sorry, 1 plus 1, you have a 2. It's just like the real part of it. But here now we include an imaginary part. That would be what? 2i. That's just, oh my god. Okay, talking about multiplication, we just have to multiply. Here we are not just going to multiply the real and the real part, the imaginary part. No, that is just cross multiplication, as we know in mathematics. You multiply a, okay, just do it. A times a1, a1 times a2, we have this. A1 times b2, we have this. b1 times a2, we have this. b1 times a2, we have this with I square. And we earlier know that I square is equals to what? -1. Exactly. Hence, okay, I'll just write it somewhere here. Hence, our a minus 1 will link the real part and the imaginary part, because these are the imaginary and these are the real. We link them up together. So have a1, a2 minus that, and on the other side you have that with respect to in terms of I. Okay. A very typical way in solving multiplication, because this one is quite big, it's quite complicated. Example of large number 15i plus 14, something like that, that would be a lot of problem for you. You can just express it into Euler's formula. Okay, where r is the modulus e to the I theta being the argument. Find the argument of this point. Take into consideration the quadrant of it. Know exact theta. First quadrant, second, third, and fourth. Knowing where you have to add and subtract pi. In the second quadrant, you add plus pi. In the third quadrant, you subtract pi. In the fourth quadrant, nothing happened. First and fourth, not is exact. Okay. If you express this initially into Euler's, okay, into its exponential form. Okay, this exponential form actually using the Euler's principle. You have r1 e to the I theta 1. Exactly, that's a basic way to simplify this. Okay, I know you're asking yourself what's happening. Okay, we take this one first. A1, B1. A1 plus B1, A1 square plus B1 square. The square root of this will make our R1. Okay, and E is equal to a tan inverse of this is B all over A. And from here we have our theta. Since we are in the first, we consider we are in the first quadrant at this point. But you're going to find your theta yourself. Because if it was in the second quadrant, you are just going to add a pi here. Okay, that's amazing. And you have our theta. We do same for the R2. And from basic principle of indices, or that, we just have to know that we multiply R1 and R2, and we add their different angles. And that save a lot of time solving this long question and bulk equation. Sorry, I got a little bit of cough. Okay, let's move then to the conjugate, because this is a critical point in mathematics. Conjugate of a complex number. That's just negating the imaginary part. The conjugate just like negating the imaginary part of the complex number. Hence, if you have this complex number, a plus bi, its conjugate will be the exact image of it in the opposite, the strictly opposite part of this pi. The opposite, because this is positive and this is negative. The conjugate will be exact image. Know that, take that into consideration. That is the image of it. Image rotation, I think now about image. When you look into the mirror, you see yourself. That's the image rotation at the point. That is the imaginary part of it. Take that into consideration, because when you look at the image, it's as if your left hand, when you shake your left hand, your symbol on the other side, okay? It's like a rotation. Okay, take that into consideration. In case you are here, the image will be here. That's good. And the angle theta, okay, z is also r e to the I theta. Hence, in this other case where theta is negative, I'm going to have what? R e to the negative theta. R e to the negative theta, because theta is negative. Yeah. Therefore, the argument of z times z bar is equals to what? That. And if you multiply this, you're going to have something amazing. That is a squared plus b squared. Exactly. By multiplying, you just multiply the a and b, we have an addition. That's how it happened. Okay, I know you're asking yourself what's actually happening here. How do we came out with this? By simplifying, you are going to have a squared minus abi minus plus okay, a squared minus abi plus a that minus I okay, sorry, here is minus I squared b squared. And simplifying this, since I squared is negative 1, okay, I squared is negative 1. Since you have negative here, negative and negative will give a positive here, you have a squared and b squared. This and this will cancel out, and we come out with this amazing part, which is equivalent to z magnitude, equivalent to z magnitude, okay, and which is equals to z squared, just like squaring this one. If you square this one, it will having something similar. Okay, let in case z being equals to r e to the I theta. Therefore, therefore z times z magnitude will be what? R e to the I theta times r e to the negative theta. Therefore, that will be simplified down to r squared e to the I theta minus that, and that is equivalent to r squared. That's equivalent to the modulo square. R squared is equals to that. Just okay, that's amazing. Moving then to division of complex number. The reason why we talk about conjugate before talking about division is because we are going to be using the conjugate principle in dividing complex number. It's not just like normal division that we just have a all over b, or like 2 all over 4. You're going to have a half. Okay, yes, a bit different. You're going to be playing around to have the exact value. You're going to have like 2 over 4 is equals to minus 4 over minus 4. Okay, and further simplifying, because you have to remove the imaginary part at the level of the denominator, and the only way to do that is to use the conjugate. Okay, we have this one. We just multiply by the exact image that is a conjugate of the denominator only. Take into consideration, just take the denominator. Good. We multiply by it. I'm going to have at the end a1 and that. Okay, I know you know how to simplify this already. We earlier did multiplication of complex number earlier. If you don't understand this part, just skip back for a few lines, few trip, and watch it. Okay, and we earlier have this as a square plus b square. We already simplified earlier. I'm not just repeat it here. I want people that understand exactly what we are doing, not just cramming or doing anything like that. Have the answer here. Okay, if you put it in this polar form, in the polar form, okay, you have r e to the I theta 1 over that theta 2. That will be r1 over r2 e to the what we subtract, that is 1 and 2. That is basic law of indices, and this is easier way, because example, if you have a very cumbersome or very complicated question to solve, I want to stay here for a lot of hours. Although if you just have to find the modules and the argument of it, it will be easier. It will easy work. That's why I like the Euler's formula a lot. Divide the module and subtract the argument. That's a basic principle. What about a complex number to a power of another complex number? Like I to the power I. Then what's this? You're going to use two principles: the exponential formula and the logarithm. Okay, let's explain it better here. Use the exponent and the logarithm. Exactly. Okay, in the exponential form, if you have z is equal to x plus yi. Therefore, e to the power z is equals to e to the x plus yi, because we brought it up in terms of e. Therefore, you can further simplify this from the law of indices. That will be e to the x times e to the yi. That's amazing. Are you seeing something? You can just take this e to the x as our r, as our modulus, okay, and this will be the normal argument. Okay, something is a bit fishy. Okay, it's going. Thank you. Let's proceed. And this as the modulus and this one as the argument. Let's take a break here and move on to logarithm before coming back. Therefore, e to the z is equals to this. We have a modulus and the argument in the logarithm point of w is equals to e to the z, that will be r e to the I theta. Exact, that is ASAP. Therefore, our r is equals to e to the x. Yeah. And because we already took it here, take it into consideration, r is e to the x. We consider this as a modulus. Therefore, our r is e to the x. Therefore, x is equals to ln r, because if you apply ln here and ln here, you're going to have x ln e, and ln e is 1. And you have x is equals to ln r. Good. Now our y is equals to theta plus minus 2 pi. Why we put plus minus 2 pi is to eliminate all those problems of quadrant. Because here you are going to be taking a broad range. Okay? Because actually, you have a 360 degree. In any quadrant, you just have to add 360 degree to it, and you're going to turn around and come back. Okay, then adding pi or all those stuff, just use this method and you're going to have the range of it. Okay, we just use that other method if you understand it. Therefore, if you apply logarithm, there's log w is equals to z, that is z log e, that is 1, times what? X plus iy. X plus iy coming from what? That is ln r, or log r. Log and ln are almost the same thing. They follow the same law. Okay? Okay, here's here. Okay, z, that is, we just have to have here. Okay? X plus iy, which will be equals to ln r, where our x is ln r, plus our y is what? I into theta plus 2 pi, 2k pi. Are you understanding why all this happening? Okay, let's come back here. Log w, okay, because here you have equals to w here. Log w is equals to z, that is equals to what? X plus yi, because x plus yi log e. Give the answer. Yeah, because this part is the same thing as that, x plus yi, and this r, we just ignore this r because we consider it as 1 for this case. That's amazing. Yeah. Moving on, can you substitute r and theta? Here you have this as a formula as the answer. Therefore, in case you have log of -1, that is ln of 1 plus I pi. Here we find the argument here of this. Therefore, z to the w is equals to w log z. This is a typical case, a typical formula. In case you have I to the I, there's a complex number to the power of a complex number. We have e to the I log I, that's a formula. Okay. The first, okay, you just substitute z and that. That will be e to the I into ln 1 plus I pi on 2. Using the formula earlier, and you have e to the negative pi on 2. Okay, moving then to the conjugation, z is equals to a minus b, and z bar is equals to a plus ib, and z bar is equals to what? A minus ib. Okay, plotting it here, the positive and the exact image. I just a recap. Okay, further simplify. We take into consideration a basic principle. If you had the z, if you have to find z and z bar, and you have the real and you have all this, what is happening? You know that this cut exactly at the middle point, that is the range, and you're going to have the formula, the real part. Let's take it back. If you have z and z bar, and you're asked to find for a and b, what are you going to do? That's the question. I'm going to use this formula. S plus. You notice that this cut exactly at the median. Okay, therefore our real part will be z plus z bar all over 2. And our imaginary part will be z minus z bar all over 2. That is a basic formula you have to know. Because at the point they might give you z and z bar and ask you to solve for a and b. You just miss out. You don't know how to do. That is a formula. Okay, from here, because it got exactly at the median, and you have that. Okay, hope you understand what's happening, and now you can solve easily equation with this principle. Okay, let's then move to a brief recap about this conjugation. The conjugation properties. This operation work. Try proving it by yourself. In addition, you have z bar plus z2 bar is equals to z1 z2, and in subtraction you have z1 minus z bar is equals to z1 bar minus z2 bar. That are the basic principle. In exponential and logarithm, you have e to the z is equal the same thing as e to the z bar. Okay, you put z bar here. And in logarithm, it's the same thing as that z bar outside. You just find the logarithm of the inner one and the z at the end. Multiplication and division. Multiplication, you have z bar, and division, the same thing. And just generalize the z bar all over. And in sine and cosine, you have that, the same thing. Okay, moving then to Demioff theorem. This is my best part. I like this Demioff theorem. I want to state that cos theta plus I sin theta to the n is equal to cos n theta plus I sin n theta. Yeah. You know about the Demioff theorem? I guess you know about it. But in case you have an arrow and all the stuff, okay, in case you have this arrow with that, I'm going to be having r to the n cos n theta plus I sin n theta. Let's just pretend this is the exact Demioff theorem, because this is what you are going to be using in terms of complex number, because you can't have a complex number without talking about the modulus, actually, because it's broad. Hence, if you start plotting the different value for r equals to 1, to 0, to 1, and so on and so forth, you are going to be having a circle, further intensifying, because it's going to be circular at a point. Okay, it's actually circular, and you're going to be having a circle like this. For theta is equal to 2, theta will be equal to 2k pi on n, and k being from 1 to 3 to n minus 1. If you start plotting the different value of k, k1, k2, k3, k4, k5, k6, 7, 8, now you see a bit as you're going, you're having a circle. I'll be coming back. You see a bit. That is what happened. And that is those points are called the n root of unity. Okay. And we come to the end of this video. In this video, we talk about what? Chapter 1, there is complex plane. Chapter 2, there is Euler's formula. Chapter 3, there is operation of complex number. And chapter 4, that was on the Demioff theorem. Thanks for watching this amazing video up to the end. If you really like this video, subscribe to the channel. Waiting for the next video that will be loading in due time. Thank you. See you there. Subscribe.